All right, so we are looking forward to hearing from Dr. Philip Lee. As you can see from the slide that he's a professor in the Department of Geography and Sustainability at the University of Tennessee in Knoxville. And he has broad research interests in paleoglacial and environmental reconstruction, LIDAR, Earth surface processes, climate and human impacts, and GIS and spatial analysis. And I'm particularly grateful for Dr. Lee joining us today because I was very excited to read his paper on the PalaeoIce tools that's recently published in Geomorphology. In addition to this, he has interests in using cosmogenic nuclides, geomorphic mapping, and his models for reconstructing glacial history on the Tibetan Plateau, the Tian Shan, and the tropical mountains of Costa Rica. So we appreciate you joining our Western US group here, even though that may not be your primary area of interest. Dr. Lee's also been interested in using LIDAR and UAVs to quantify Earth surface processes such as stream bank erosion, gully erosion, and hill slope erosion. So take it away, Philip.
Okay. First of all, many thanks for the invitation and introduction. I have to say my study is mainly on Tibetan Plateau. That's because my education background, but definitely interested in, North America, if I have a chance to work on that. I want to give a talk about the PalaeoIce tool I just developed as a published, to reconstruct paleoglaciers using geomorphic evidence and digital elevation model. I think especially for this group, I probably don't need to say a lot about this. The paleoglacial reconstruction studies, right now we did a lot of advanced numerical dating, especially cosmogenic dating, right? So it's kind of revolutionized our understanding about glaciers. We have global data sites like ICED or X4H by Jakob. Another perspective, we also have advanced technology to detail mapping of glacial landform based on high-resolution imagery, Google Earth, DEM, GIS, or even AI, machine learning, all kinds of things. The third perspective we work on, is from the modeling approach. I think traditionally, we kind of manually reconstruct paleoglaciers, but right now, we have a lot of modeling work can do that. Basically, we have two type model. One is kind of like based on glacial landform, and then using ice surface profile model, a simple one to reconstruct paleoglaciers. We definitely have a lot of work on more complicated coupled mass balance glacial dynamic models. You can see these slides. We have a lot of different dimensions, a lot of complicated parameters. It's probably not the hand of regular geomorphologist people to do. But the presentation I gave is mainly focused on, using geomorphic evidence to an ice surface profile model to reconstruct paleoglaciers. I think all of us know, this flowline model. So basically, in an ideal steady state, condition, the ice surface is like this. It's like this along the flow line. So this photo indicates flow line on glaciers is kind of like close to glacier center line. And then when this situation, we have this shear stress functions, can describe by this simple function here. And then the shear stress of glaciers is roughly about 100 K per, but they have a range from 50 to 150, but some study also indicate maybe up to, 190 or even 200. In mountain glaciers, one thing we have to consider is because the glacier is constrained in the valley, so the side of valley also have an impact on the shear stress. So this is mainly described by a shift factor. Basically, we use this equation to calculate the shift factor. But I think another scholar is another Lee, it's not me, also, do some statistical methods, based on some, theory shape factors based on different dimensions, and then create this kind of fitting model, to fit shape factors. So all of this, it's kind of basic for us to do. But we know this, equation or ice surface profile for a long time, but it's really bring us to use this in geomorphology. It's Ben and Houghton's work in 2010 to develop this Excel-based, flowline model. So this is a screenshot of this Excel-based. So you can say, they actually create two profiles. One is simple one, another is more complicated. But basically, in this case, we can put bed elevation, shear stress, shape factor, and then also have some called target elevation. Is for some location, we may know the height of ice. And then we have to manually adjust, individual values to fit all these target elevation. So you can think about, this is great too, right? So we can kind of explore this, but need a lot of manual work. We have to have the elevation profile from DEM and then put in Excel and then output back to GIS to do that. So it's definitely a need. We can directly run this in GIS model. So last week, Caleb gave a talk about this Glera model developed by Paleoglaciers in 2016. So basically, you can say they have a set of tools to do ice thickness calculation, and then to do surface interpolation, and also can derive shape factors, adjust shear stress, all kinds of functions. However, when we use that, we still need a lot of effort. So for example, the tool only provide one to derive the main valley flow line. So basically only along the main valley. So they cannot delineate the tributary flow line. So basically for simple small glaciers, it's okay. But if you have more complex glaciers, we have to digitize a lot of flow lines. Another thing is this tool, we use a default value, for example, 100 kPa or the stress. Or you can specify a specific value to do the simulation. But a lot of cases we have to test a lot of different values to see which one actually fit the the scenario. If you want to change shape factor, we also can manually input the values. We can also provide cross sections manually. So that's a lot of manual work. So I think Caleb did a lot of good work, right? But my student work on this, we realized they have a lot of, difficulty to do this. I think that's one way I try to develop this new tool. Another tool you probably know that is James and Kervik develop a Volta toolbox. It's a similar one, but this one actually to estimate the ice thickness and volume for modern glaciers is basically based on the ice surface and the polygon to know the thickness of the ice. So this is based on a revised flowline model, so slightly revised based on the original I showed you earlier, so that the result indicate this provide a better ice thickness estimate. And then this one actually also provide a centerline delineation method, can be used to derive both main valley and tributary valleys. So that's great. But the thing is, we cannot directly use that for the paleo reconstruction. But I think the advantage is we have the centerline, and then we can derive the thickness for modern glacier, and then we can remove that from the topography for the paleo study. So basically, the motivation for me to develop PalaeoIce is want to develop an automated method. The first thing is I want to develop, flow lines for both main valley and tributary valleys. And also if you have modern glaciers, so we can incorporate the flow line with the center lines from glaciers. And also can, remove the ice thickness if you have modern glaciers automatically, and also be able to optimize shear stress and then automatically derive shift factors. So basically the idea is we want to automate all this process. So this is a toolbox I developed. Basically you can say this mainly includes three parts. One is the flow line creation, another is to remove the modern glaciers from topography, and then the third one is to PalaeoIce reconstruction. But definitely for each part, I have different tools for different kinds of scenarios. The toolbox source code all in the GitHub page. So basically, you can download the file. I also post a test data set there. Welcome any comments, right, to continue improve that. So I will introduce these individual tools, and then we can have time to discuss or some comments. So this is the area I used to test this tool. That's one area in the eastern Tian Shan. Basically, there's a glacial stations established in the 1959. So basically, this area is kind of like the most studied area in glaciers, geomorphology of glaciers in China. So you can see they have a lot of cosmogenic dating from later Ice Age moraine all the way down to the MS2 or last glacial maximum in this valley. They also have the ice thickness measurement for this glacial number one. Actually, right now it's two glaciers. They call this glacial number one because there used to be one glaciers. And then also have some mappings or other kinds of features in this area too. So basically, the first part is to generate flow line. In this case, I consider three kinds of scenarios. One is if you have modern glacier, or sometimes we have paleoglacier, but we have this polygon boundary, for example, later ice age. In this case, we can simply just using the water centerline method to generate flow line. For some other case, we only know the end marine, but we don't know the whole boundary. So I created a flow line method using the hydrological stream network analysis. But for some cases, we may have both glaciers and end marines. So we may need to combine flow lines from the above two with the center lines. Based on the work I did in the past year, the water center line actually doesn't work well for very complicated glaciers. So right now I kind of developed some new tools to continue to handle big and complicated glaciers right now. So that's one for the water too. The water, if you know, is based on a glacial axis, is the longest axis method to derive the initial center line and then have a kind of upstream area to decide the tributary. But this method has some limitation. For some small glaciers have much wider length than the length. In this case, if the glacier are much wider, the center line will from one end to another end. It's not, it's kind of cross the flow line. It's not the real flow line. So basically, I revised the code. In that case, it's just derived from the highest point to the lowest point. Also revise some other part. So this figure is probably not clear, indicate some center lines generated. I think that the white color is indicate I revised code. So you can see this small glacier actually is okay here. But the red line is the center line generated by the original waters. You can say this is not, reasonable center line. So if we only have end marine, for example, here we have one marine here, but we want to know the, the flow line for the whole glaciers. We don't know the boundary, so we cannot use that water method. In this way, we use hydrological analysis. Some of you may know need to fill DEM, flow direction, acclimation, stream, kind of thing. The traditional GIS derived stream network include a lot of small streams. So basically the idea is I develop another parameter, try to remove the small streams. This figure indicate that because, for example, S is the traditional GIS using the threshold value to define the start of the stream, but they don't have method to define the end of stream, right? So basically we have a parameter to decide, the stream is at least this big, right? So in this case, we can remove a lot of small streams. And then definitely glacial flow line is more smooth than the river because river may have, a lot of sharp turns. So we smooth and remove some big turns. So this figure indicate, the flow line generated, after remove this, after smooth. So you can say it's okay, it's not too bad, but when they close to modern glaciers, because glacier topography, we know the center of glacier, especially in the ablation zone, is higher than the edge, right? They will cause the streamline delineation, toward the boundary of glaciers. For example, this one or this one, they are not follow the center of the ice. So that's required the need to kind of combine the flow line and the center line. So the idea is we remove all the flow lines derived within the glaciers and then replace that with the center line we derived. It's more complicated because something you have to think about how to connect these two systems. But this line, you can see the left side is the original flow line. The yellow is kind of the center line. So you can see they are not aligned well. And then after this process, we kind of remove the flow line within glacier and then replace with center line. So it looks much reasonable or much better than, that method. So after that, definitely we can, if we have modern glacier, we need to remove the ice topography. The first step is based on water to estimate the ice thickness, and then simply subtract this from the DEM. So this indicate, you can see the water ice thickness by this colored, things. And then you have DEM on the background, and then basically it's just subtract this to remove that. So we have this background topography. So the third step is to do the PalaeoIce reconstruction. In this case, I basically developed two tools for three scenarios. One is, we may have paleoglacier, we actually know the boundary, for example, late ice age, right? And then we can use this boundary to constrain the reconstruction. Another case, probably more common for old features, is we only know the end marine there. And sometimes we may know some target, features, for example, trim lines. We know the local height, right? But it's not necessary we know that. So basically the idea is, we have this looping process to optimize the searches to fit all this evidence. This flowchart indicate, I probably don't have time to describe individually, but they start as a glera using default search stress and then shape factor at 1 to derive the thickness and then interpolate the surface. So basically that part glera is done, right? And then after that, we use the surface raster to derive the shear stress. And then using the polygon to derive the shape factor. And then we compare this shear stress with the initial shear stress to see whether they are same, right? If they are very different, we have to go back to recalculate until the shear stress reach a stable value. So in this case, I use the difference of less than 0.5%. But if you have these paleoglacier outlines, this will help us to do the surface interpolation because we know the boundary, and then can be faster derive the shear stress. Can also help us to derive the shape factor. So basically, come back again, we can speed up to derive a more stable, shear stress like that. But if we have target feature, for example, we have trim lines. So basically, we are using the simulated boundary compared to this trim line until they reach the minimal distance. So in this way, we have a better fit for the field evidence. I will show you something. This is the later ice age reconstruction in this area. So in this case, we have the boundary, right? We have this, outline of late ice age, and then we can reconstruct that. You can see here, I have this default shear stress, but also have a minimum maximum value. So you can adjust the default value. The maximum is 200K. Maybe you think, oh, it's too big. You can reduce to 150. In this way, may be able to speed up the process a little bit. So this is the one is we only have this end moraine without consider any kind of trim lines. So you can say this reconstruction actually gave us a much thicker ice. And then shear stress 173. So basically this is too big, compared to our evidence too big. And then the last one is if you have this right line is a trim line, right? If we input this trim line, so basically the reconstruction will fit, to find the shortest distance, average distance to this trim line. In this way, we can see the ice surface is kind of constrained. It's not that thick. It's not that thick. So another way is kind of validate to check the accuracy of this. Basically, I did is for this glacial number 1 because they have this ice thickness measurement, and then we compare the reconstruction with this major thickness. So you can see they definitely have a lot of spread, right? Very scattered. But the average value or the regression value is not too bad. The average is from 1 meter to 4 meter, difference, compared to the measurement. Relatively, it's less than 10%, about 5% difference. And then another way I compare is water and the reconstruction, because water is using the surface, the ice surface topography to estimate the thickness. And then PalaeoIce is using the bare ground to estimate the thickness of the paleo ice surface. So both methods are based on flow line. You can expect they are kind of similar. The result indicate, it's definitely pretty close, right? The average difference only about 1 meter. Only some small glaciers like here, some small glaciers have some rather big difference. The reason is because water using some surface slope or other constraint to interpret the surface. But PalaeoIce, because we don't know the surface, original surface, we cannot assume any of this. So I think I'm basically done. Right now, during the break, I kind of work on the late ice age reconstruction for the whole extension we mapped. This map by my student, Nancy Lee, right now in Texas State. So we have these 4 areas I want to show you. Roughly, we have 640 late ice age map, and then corresponding to about 1,400 modern glaciers. So you can say this is one region, the late ice age mapping here. There's another region, the Cardiac region, the glacier much bigger, so you can see the flow line we derive actually is not too bad. And reconstruction kind of reasonable. I think that's all my talk. I definitely look forward to hear more comments or suggestions to improve this toolbox. Okay.
All right, excellent. Thank you, Philip. That was really great to hear. Since we do have just one speaker, we're only hearing from Dr. Lee today. We have some time for questions, plenty of time, I think. Looks like Caleb has his hand up. Go ahead, Caleb.
Dr. Lee, thanks for a great talk. I found some time earlier this week to use your tool, and I want to say it's spectacular, and I wish it was around a couple years ago. Because as you mentioned,
It is actually around about 2 years ago.
Well, published. Anyway.
3 years ago, maybe. Yeah, but published this year.
Yeah, it's really exciting. I was curious if you could speak to, have you tested this with any glaciers that are any Piedmont glaciers? In particular, some of the glaciers I've been working with in Alaska have a large Piedmont, so they've got a rather ovular terminal moraine, and it was giving me some funny things. So I was wondering if you had tried this with Piedmont glaciers, or maybe terminal moraines that are larger rather than just constrained to a small valley bottom, or if you had any suggestions there.
I have not checked the Piedmont glaciers. I can imagine Piedmont glacier may have some problem because, you reach outside when you have ice surface and then you interpolate, you didn't reach the boundary, right? So that may be some issues. One way to solve that, or maybe you can check that, is if we can provide a boundary, for example, we know the moraine, right? So the boundary, just like, using the trim line to constrain, they cannot go over there. That's maybe a solution. But that's definitely an issue, we need to check. Another issue is the ice sheet, right? So basically, this is mainly for the valley glaciers, right? So if you have ice sheet,
yeah,
you have multiple, outlet glaciers. I think they have some issues there too, right? But maybe we can test to find some solution. Maybe ice sheet, for example, we can just treat this as different, valley glaciers.
Great.
If the Piedmont work, this can work too. Yeah.
I'll send you an email soon. And I just had a quick other question. For deriving flow lines, did you have, you have the minimum contribution area before a stream will essentially start for your flow line, and then you also have this tributary ratio. Do you have you found any that work particularly well? Are these dependent on the size of the glaciers, or is there some ratio you should be looking at depending on the size of your glacier?
Mm-hmm. Yeah, that's a good question. The default value is based on water. So basically, the author of water actually tests a lot of modern glaciers. And then they say, okay, that 20, or I think it's 120%, 130% is the best value for modern glaciers. But I'm sure that when glacier getting bigger, this ratio may not work. So you can say the default value when I use for paleoglaciers, I think I use 5% rather than 20%, right? So yeah, that need a test, need something test. I think maybe different area will be different. Yeah, but that's a good question. Maybe you can find a better solution for different scenarios. Mm-hmm.
Great. Well, thanks for indulging me there on the weeds, but I look forward to testing it, and I'll be in touch soon, I'm sure.
Yeah, just test, if they have errors, you let me know, and then, we can fix it. Especially for the big glaciers, right? So because the demonstration I gave you is mainly kind of small glaciers, right? So if you have more complicated glaciers, I think they may have more problems.
All right, it looks like we have another question from Doug Clark. Go ahead, Doug.
Okay.
Doug, I think you're on mute.
There. Okay, can you hear me now?
Yes.
Yep.
Yeah, okay. Thanks, that was a really interesting talk. I have a much more of a practical question. Our university is shifting over from ArcGIS and ArcMap into ArcPro, and that's one of the issues with Glare. Glare has not been updated. I contacted the authors on that, and they're not going to. So is yours, do you have your code available as something to go into ArcPro as well as ArcMap?
Yeah, the code developed is based on ArcGIS 10.7, but I think I kind of try to manage the code run for both. Actually, ArcGIS Pro is more efficient. Sometimes ArcGIS 10 have some memory issue if you run a lot of glaciers, and then ArcGIS Pro actually run faster and then can solve more problems. So basically, all these tools can run in the ArcGIS Pro.
Okay, that's great to know. I'm hoping to incorporate this in the next time I teach my glacial class.
Yeah, okay.
Other questions? Maddie, go ahead.
All right, there we go. Hi, that was an awesome talk. I just had a question about have you ever compared the interpolation of the glacier surface between the glare tools and then the tools you developed?
Frankly, basically, they are the same, right? If you use the only thing PalaeoIce did is, because for glare, you have to, type in shear stress, right? So for example, 100K.
Mm-hmm.
Then you may provide some shape factors, right? Because the default is 1, right? So, but PalaeoIce is basically we simulate, a better or a fitable shear stress, but internally calculation is the same.
Okay.
So basically it should be the same, but I didn't compare because for the PalaeoIce too, it's always because we do the shape factor for each section, right? So, but if you run the glare, you're probably just using 1, so that will affect. Yeah.
Okay. All right. Thank you.
Welcome.
Any more questions? Leif, go ahead.
Sorry, I'm not very on my emoji game today. My question is, have you compared it to, for example, the global ice thickness reconstructions of like Daniel Farinati for modern glaciers? How does it look compared to that?
That's a very good question. That's one step I really want to do. I think the initial work, for example, the Tianshan one, the glacier number 1 compared to actually, that one contribute to this global ice sheet data set. But so you can see the result is about 5% difference. That surprised me because other studies suggest they have to be 20%. Anything below 25% is good. So that's one thing I want to do is to, have all the glaciers, right? Have major ice thickness, and then to run that, and then to do the comparison, but have not been able to do it. I think I did one glacier for Tianshan, and then one of my student did another glacier on the Tibetan Plateau. The results are consistent. Looks 5 to 10% difference, but definitely need a wider comparison, to do that. Hi, Nancy.
Hi, Dr. Lee. I just want to say you did a great job on presenting your fabulous work on this PalaeoIce model. Yeah, I enjoyed the talk so much. And I want to hear your thoughts on the application of this thickness calculation and PalaeoIce reconstruction. What kind of downstream applications you think that can be derived from this tool? Like, I'm thinking in the direction of like water resource and things like that, some applications.
Yeah, this is definitely a good question. What I'm thinking is I want to provide a tool because the idea to develop this is because of pandemic. I cannot go back to China, I cannot go to the field, but I have some students work on some work. They want to use Glera, but they don't know how to set up parameters. And then I'm thinking, okay, maybe I should take over to develop some tools to automate this. So definitely one application is the water resource, right? For example, later ice age, how much water lost since later ices, or how much water lost, since the last glacial maximum, right? So we don't know. If we have these two, if these two can be validated to say, okay, it's reasonably well, so we definitely have a better idea about this. Another thing is, I didn't talk about this. I think Caleb last week talked about, we have ELA, construction tools, right? So the ELA construction, a lot of our previous work is based on the DEM, right? So, but we know the DEM is not the, paleo-ice surface. So if we derive this, paleoglacial reconstruction surface, we can derive better ELA, and then we can have a better climate, kind of paleoclimate reconstruction. I think that's something in my mind right now. I think they may have other applications. For example, compared to the global ice thickness data set, if we compare the right now, right, the modern glaciers, they have ice measurement. If we have reasonable comparison, and then we can say, okay, maybe that indicate the LGM construction also reasonable, right? For example, some initial work indicate that the difference are mainly for smaller glaciers. If the glacier getting bigger, actually the results getting closer. So I think that needs some work. If we can prove that, we may have a better, idea about, glaciers in the past. That's something in my mind. That's definitely a lot of things from this group may think about other applications.
Yeah, all sounds so interesting. Yeah, thank you.
You're welcome. But this work is based on your later ice age map, right? So
I know, I need to give you more.
yeah, provide me more.
All right. Any more questions? Leif, go ahead.
I haven't tried out your tool, but I'm just wondering, in ArcGIS, how does it work for multiple glaciers? So if I had 20,000, what would happen if I clicked compute?
Yeah, let me share the screen. I do have ArcGIS 4 in my. So I try to run this analysis. Can you see my screen right now? So basically the computer, the program is have a looping process. If you have multiple glaciers, they just run multiple glaciers over and over again. The only thing we have to be careful is ArcGIS have limitation because we have a lot of computations. If you run, for example, 20,000 glaciers, I'm sure that will crash. So basically, if you divide this large area into smaller areas, my experience is if you have roughly about 15 or 2,000 pixels times 2,000 pixels, we should have no problem to run the whole tool from the beginning to the end, no problem. But if you have more than that, you have to divide this into smaller regions in order to make sure the model can run. But that's probably also related to what type of computer, what type of memory you have for the computer. So. Yeah. But if you have any questions, you can send me email. In my GitHub page, I have some suggestions how to run. I think all these things. Whatever people tell me the problem, either I solve that or I write this down. Okay, don't do this.
Oh, very good. Okay, well, thank you again,
thank you very
Dr.
much.
Lee. That was really great to hear. I know I'm just one of many in the group here who are excited to do some more experimentation with your tools. And we're excited that you invested so much time in this work. And yeah, we're looking forward to doing a lot more and hearing a lot more. So let's thank Dr. Lee one more time here.
Thanks.
Oh, thank you guys. I definitely look forward to to see more of this work used in the US.